Hello, and welcome to today's video of electrical materials, where today we will be covering thermal conductivity. Thermal conductivity is defined as the rate at which heat flows through a material under steady-state conditions, when there is a temperature difference across the material. It is important to note that for metal materials, as temperature increases, so does its thermal conductivity. Let's go ahead and look at some common metals and their thermal conductivities. Looking at this table, we have a list of metals and their thermal conductivities. Although this table is not included in the FE Reference Handbook, it is important to note the conductivities since these are metals that are commonly used in questions for the exam. Looking at this table, we can see that silver has the highest thermal conductivity, with 429 watts over meter Kelvin. If we were to compare this to steel, which only has 50.2 watts over meter in Kelvin, we would be able to make the claim that silver is the better conductor for heat. Another metal with a high thermal conductivity is copper, which has 401 watts over meter Kelvin. Now that we've looked at this table, let's go ahead and look further into how we can define thermal conductivity. Another way to look at thermal conductivity is mathematically, using Fourier's law of conduction, where we have the rate of heat transfer, denoted as Q dot, is equal to negative K, our thermal conductivity, times A, our surface area perpendicular to direction of heat transfer, multiplied by dt over dx, which is our temperature gradient across the material. Let's go ahead and clear the board to look at an example. For our example, we have a flat rectangular slab has a thickness of 5 centimeters with a cross-sectional area of 1 meter squared. Calculate the rate of heat transfer if the material has a thermal conductivity of 20 watts over meter Kelvin and a temperature difference of 50 degrees across the material. So in this question, we are asked to solve the rate of heat transfer, so Q dot, since we are already given our thermal conductivity. So let's go ahead and make a note of our given information. We can start off by noting that we are given our thickness, which we can denote as X, as 5 centimeters. And we're going to go ahead and actually convert this to meters as per our previous slide. So we have 0.05 meter. And we are also given our cross-sectional area, so A, which is equal to 1 meter squared, and we do not need to convert this. We can note that we are given our thermal conductivity K, which is 20 watts over meter Kelvin. And lastly, we have our temperature difference, which we'll write as delta T, which is 50 degrees Celsius. And we need to convert this to Kelvin, and we can do so by adding 273, which gives us 323 Kelvin. Now that we've noted our values and made any necessary conversions, we can see here that we aren't exactly given our temperature gradient. We are given our temperature difference and our thickness. So in order to solve for our temperature gradient, we can write that our temperature gradient, dt over dx, is actually equal to our difference in temperature divided by our thickness x. So knowing this, let's go ahead and set up our formula. So for the rate of heat transfer, Q dot, we can equal it to negative K, so 20, and writing our units, watts over meter K. And we multiply this by our area, so 1 meter squared. And then our temperature gradient, which we can write as 323 Kelvin, divided by our thickness, 0.05 meters. So now that we've set up our formula, let's go ahead and clear the board to continue to solve. So continuing to solve for our rate of heat transfer, we can go ahead and simplify first by dividing 323 Kelvin by 0.05 meter. So we have negative 20 watts over meter Kelvin multiplied by 1 meter squared. And after dividing these two, we have 6,460, and we have our units as Kelvin over meter. So because our area is equal to 1, this makes it easy when we are looking at our units. So we can go ahead and just cancel this out since it's 1. And we are left with multiplying negative 20 by 6,460. But before we do that, let's go ahead and also note our units that cancel out for our area. So meter squared is canceled out by our meter here and our meter here, since they're both in the denominator. And now we can continue to solve. So continuing to solve for our rate of heat transfer, if we multiply negative 20 by 6,460, we are left with negative 129,200 watts. And this is because our K canceled out here. This concludes our video on thermal conductivity. Thank you for watching.